Good afternoon. My name is Toni Pasanen and I work in a company called ElFys as a senior project engineer, and I'm also one of the co-founders of the company. In this presentation, I will introduce you our latest product, the Black Silicon 4-quadrant photodiode, which has been optimized especially for the near-infrared wavelength region. Let's start with a few words about us. ElFys was founded in 2017 after long-term research done on photodiode technologies to commercialize the inventions done at Aalto University. This commercialization we have done quite successfully. We have already more than 90 customers in more than 20 countries worldwide, which we support both by our direct sales and customer support as well as via our distributor network. We are based in Finland, where we do our research and development and production up to certain volumes. One could call it a semi-mass production or pilot volume. And for the applications that require the highest volumes, we have partnered with the fab partner, which is also located in Europe. So what ElFys does is that we provide photodiodes with sensitivity that exceeds anything seen before. And what this means in practice is that the photo response of our photodiode products is as high as one can ideally get. On this graph, you see the photoresponse as a function of wavelength, and with the dashed line, I have highlighted the performance where the external quantum efficiency is 100%, meaning that every single photon gets absorbed and every single charge carrier generated by those photons are also collected as an electrical signal. And as you see, our photodiode's performance follows this ideal line very closely. The EQE is actually more than 99% for the whole wide range of wavelengths shown on the graph. And this data is not only measured by us, but it has also been verified by world-class metrology institutes, including the Physikalisch-Technische Bundesanstalt here in Germany. Another interesting property of our photodiode technology is that the photoresponse also remains high for a wide range of angles in addition to the wavelengths. So for as high as 60 degrees incoming angle, you still essentially get the same photoresponse as shown on the graph, and for 70 degrees angle, the EQ is still more than 90%. This very high performance then of course brings many benefits in different applications. The most obvious one being maybe the increased signal-to-noise ratio, as the dark current is at the same level with other photodiode technologies. Also, since the sensitivity is very high, you may be able to detect light, which is that weak that you haven't been able to measure it before, but with our photodiode technology, it is possible, or you are also possibly able to run your LEDs or other light sources in the system with the lower power. Also, since you will get the same amount of signal with a smaller detector area, the optical system design becomes more simplified. What also differentiates us from other players in the field is that we are quite flexible in providing our customers with customized solutions according to their requirements, which is something the big players in the field are often not that willing to do. We also provide certain processing services, which is one way how our customers can benefit from our IP and technology. And also licensing our technology is one method. So the topic of this presentation was near-infrared detection, and the reason for that is that there are increasing number of applications operating in that wavelength region. What is common for all of these applications and basically almost any application as well is that typically some level of high sensitivity is needed, and often the higher the photoresponse, the better for the application performance. But at the same time, also the photodetection speed should be fast. So there is clear demand for photodiodes operating in the near-infrared region that have both high sensitivity and high speed. What is also common to all of these applications shown on this slide as examples is that many of these utilize the neodymium-doped yttrium aluminum guarded laser that emits light at 1064 nanometers, and that is the reason why we will be talking about this wavelength also later in the presentation. So what have we done at ElFys to answer to this demand for photodiodes of high responsivity and speed? So first of all, for the response, we apply this kind of our patented black silicon nanostructure on the device light entering side, which eliminates all the reflective losses from the surface. And with that and a few additional tricks, we achieve the very minimal optical and electrical losses, resulting in more than 99% external quantum efficiency over the wide range of wavelengths as shown in the graph. But what is also evident from the graph is that when you go beyond 1000 nanometers or so, the photoresponse starts to drop, which is because of the natural silicon material properties. So the material starts to become transparent and not absorb light that efficiently. This is what we can see from this graph. So you see the absorption depth as a function of the wavelength. And if we look at the wavelength of 1064 nanometers, you can see that the absorption depth is in the order of millimeters, while the silicon chip thickness is typically some hundreds of micrometers. So the obvious way how the responsivity could be improved is by increasing the detector chip thickness. However, at the same time, the detector would become slower. So there is clearly some optimization needed between these two parameters. Let me introduce you the result of our optimization work, which is the black silicon 4-quadrant detector that you will see here. In the heart of the component is the photodiode chip that you will see in the middle. The active area, which has 14 millimeters diameter, is divided in 4 equally sized quadrants, which enables to get positional information on the laser spot hitting on this active area by comparing the current from each of these 4 different quadrants. In front of this photodiode chip, we have a glass window that has a two-sided anti-reflection coating, which is optimized for 1064 nanometers. And underneath the chip, we have an optional heater, which can be used to enhance the photoresponse even further by heating up the silicon chip. Let's have a look on the most important optoelectronic characteristics of the component. Here you will see first the external quantum efficiency and photoresponse of the bare photodiode chip. The external quantum efficiency of the chip is very close to 100%, up to around 1000 nanometers, which is expected for our expected and typical for our black silicon technology. And the maximum photoresponsivity is obtained at 1010 nanometers, which is 0.79 amperes per watt. When this chip is then packaged and the window is put in front of it, onto it, we can see that actually the package in practice does not change the performance at all for the wavelengths more than 1000 nanometers for which the anti-reflection coatings have been optimized. And at the wavelength of 1064 nanometers, the photoresponse is as high as 0.64 amperes per watt, which is more than 30% improvement compared to the other state-of-the-art components for the same purpose. Interestingly, the properties of the glass window in the package are such that there is another performance maximum at 575 nanometers. So in practice, the component could be used as such also for this wavelength region. As discussed, also the fast of the photo detection is very important, and on this slide we focus on the rise time and fall time of the component, which are typically used to characterize the speed of the detection. So we have measured the speed of the detection at 140 volts reverse bias over 50 ohm load resistance, and both the rise time and fall time are found to be 12 nanoseconds. Since this component is used to determine the location of a laser spot, it is of course very important that the photoresponse is equally high in all of the quadrants and also each of the points in each of the quadrants. So the uniformity is very important. Of course, also the crosstalk is another important parameter. So when the light spot is hitting one quadrant, the signal coming from the other quadrants that are not illuminated should be as low as possible. On this slide, you will first see the reflectance map of the black silicon surface on the photodiodes for 1064 and 550 nanometers, and for both wavelengths, the reflectance is well below 1% with the maximum 0.2% variation. This high uniformity then translates also in good uniformity on the photodiode level as the photodiode current or responsivity. So the response uniformity is typically for 1064 nanometers 0.9% and crosstalk around 1%, and for the visible light the response uniformity is 0.2% and crosstalk less than 0.1%, so which are very good numbers, and the uniformity is defined as shown on the slide. On the right hand side image you can see another important point. So what happens when light is hitting in the gap between these photodiodes? And as you see, the collection efficiency is also there, only 1 to 1.5% lower than within the actual quadrant areas. So these regions, the gap between the pixels are not, the signal is not lost there, but it's also collected. But of course the signal is then divided in the two quadrants that are next to each other where the light spot is hitting. As mentioned, the applications for this kind of 4-quadrant detector are laser spread alignment, essentially. One example of such applications is guided munition, which is shown here in more detail as example. So how this application works is that there is a soldier in the battlefield who has a device emitting light from the YAG laser at 1064 nanometers, and he is targeting the enemy target with this laser, so-called painting the target with the laser, and the reflected light from the enemy target is measured with a 4-quadrant detector that is sitting in the nose of the missile. And by comparing the current coming from all of these 4 quadrants, the missile then knows how to adjust its flight path to hit the target. And typically this good zone where to launch the missile is rather limited due to various different reasons. With our increased sensitivity, the good zone can be enhanced because the lock-on distance can be increased by up to 30% compared to state of the art, which makes it both safer for the soldier in the land because he or she can be further away from the enemy target, and also the accuracy, hit accuracy of the missile or bomb is increased. And of course, there is typically many different kind of disturbance in the air in the battlefield, such as smoke or dust, and the improved sensitivity also helps to improve the accuracy in these kind of situations. As a summary of the 4-quadrant black silicon photodiode product, I show here a snippet from the datasheet of the product. The main point to highlight here is the responsivity of 0.64 amperes per watt at 1064 nanometers, which is more than 30% improvement compared to the state-of-the-art components. The full datasheet is available on our website, and of course you can reach us and we will share that with you. In addition to the Quadrant product, we have also a bunch of other photodiode products available as standard products. In the so-called PD series, we have various different sizes of single pixel pin photodiodes available, packaged in different types of packages, including different ceramic packages and TO cans. And these are meant mainly for high precision light and radiation detection applications, such as different types of measurement systems and analytical instrumentation. And then in the surface mount series, we have photodiode components available, which are packaged in surface mount type of package and coated with optical epoxy, and they are meant mainly for high performance wearable applications. With that, I would like to thank you for your attention.